So, good morning. In our last class, we have been discussing about the filter designing and how the placement of the poles and the zeros they were affecting the uh, amplitude response of the filter. Now, before going ahead, let us understand about the filter responses and how the placement of the poles and the zeros can help us in designing various types of filters. Okay. So, if you look over here, what we are having broadly five classes of filters. You can say conventional filters. So, first one is the low pass filter, high pass filter, band pass filter, band reject filter, and notch filter. Okay. Now, what is the frequency response of the low pass filter? If you see the low pass filter, it is having a high value from DC component to FC. FC is the cutoff frequency of the filter. Okay, and in any digital filter, we know that the frequency component it would vary from 0 to pi. Okay, ideally it should be 0 to 2 pi, but we usually look into the frequency domain aspects in the positive side. Okay. However, from our previous knowledge, we know that these frequency characteristics they also what do you call extend in the negative frequency domain also, or if we extend this to 0 to 2 pi also. So in the pi to 2 pi region also there will be an extension of this band. But for the sake of understanding at this moment, we will be looking into the frequency response in the range of 0 to pi. Okay, so a low pass filter it is having a frequency characteristics like this. From 0 to fc you will be having the pass band, and then fc to pi it would be a dead zone. Okay, in the high pass filter it is just the opposite. Fc to pi we are having the high pass component, and 0 to fc we will be having the dead component, dead zone. Okay, or we can say null zone. Then we have band pass filter. In the band pass filter, what happens? There would be two cutoff frequencies, FC1 and FC2, and within this FC1 and FC2, we will be having the pass band, and all other region will be having the stop band or dead zone. Okay. Then the next type of filter, it is the band reject filter. In the band reject filter, we will be having from 0 to FC1 pass band, then FC1 to FC2 we will be having the dead zone or the null zone, and in the third zone FC2 to pi will be again having the pass band. Okay. Now in the notch filter, what we have, we will be having the pass band from 0 to pi, but at the FC critical frequency there will be a 0. So that means what happens over here is that here the amplitude value or the gain value at FC it would be at least a by root 2. Okay, or we can say minus 3 dB gain. Why it is taken? It is taken because at the cutoff frequencies the power of the signal which we are filtering it should get down to the half of the maximum power, okay, of the signal. So this is the reason why we choose FC as the this A by root 2 as the cutoff frequency gain. Okay. Now to better understand how the placement of the poles and the zeros they play an important role, let us first take the example of the low pass filters. Herein you will find that we have taken four cases: case 1, case 2, case 3, and lastly case 4. Okay, and lastly case 4. So In the case 1, what we have, we are having a single pole filter. For the sake of understanding what we have done, we have placed the pole on the real axis. Okay. So please be reminded that I have drawn this z plane without this axis, real z and imaginary z, right? But when you are writing in the exam, please write this, otherwise there will be deduction of marks. Okay. So all the axes should be labeled properly. Now if you see over here, we have placed a single pole. Okay. Now how it is affecting the amplitude response, let us see that. If you see, we have told that we are interested in the region of 0 to 0 hertz to pi, or you can say 0 radians to pi radians. Okay. Now consider that after the placement of the pole, we are looking onto the frequency component from the top, on the frequency axis from the top, right? So basically what is there? We are having, say, a table. On the table we have a rubber membrane, and we are watching this rubber membrane from the side, which is basically from the top of this here. Okay. So when we see this, so say this is 0 and this is pi, right? So if you look at this, so when we place a pole near to the frequency axis, which is basically nearer one most is the zero frequency. So what will happen? This rubber membrane, it will extend like this, and over here we will be having certain gain component. Okay. So this is what we can see over here. At zero frequency, we are having a high value. Okay. So if you consider this thing 0 to Fc and minus of Fc. So over here we are having the maximum value, and as we move towards the pi, there will be a decrease in the amplitude response. Okay, there will be a decrease in the amplitude response. However, if you look into the distance component over here, this is finite. Hence, modulus of h of z, it will also be a finite value. Okay, it will also be a finite value, and hence at this location, if you see, there will be some frequency components which will be passed, okay, which will be passed by the filter. Okay, which filter? The filter just I have shown in the case 1, right? Now we have looked into this. So if you see what I have done in the next step, I have just reversed this scale, because when we talk about the classical filter representation, passband representations, so we start with 0 and in that high frequency components. Okay, so we have just reversed it to get the ideal plot, ideal natured plot. So as I told you, at a by root 2 we will be having the cutoff frequencies. A is the maximum amplitude, and a by root 2 will be finding out the corresponding Fc1 value, and it will give us the information Fc value. Now, as I told you, in many cases, this residual amplitude at the pi radians is not recommended. Okay, why it is not recommended? It is not recommended because having some gain at pi radius means at the FM value some signal components will be passed. Even though we are saying that we are considering A by root 2 as the cutoff frequency, still there will be some frequency components from the original signal which will be passed to the filter components. Okay, now this may lead to some interference. If you are working with very low amplitude signals, it may create some problem over there during the analysis. Okay, now due to this reason what we can do, basically we want to stop the frequency component at pi. Okay, we want that at pi the frequency should be completely suppressed. Okay, so to achieve that, what we can do, look over here, we have just placed a 0 at pi. So when we have placed a 0 at pi, what it is doing, it is suppressing the frequency components that will appear at pi radians. Now, if you look into the amplitude response, what we have at A, we are having the gain, and then it slowly dies down, and at pi it becomes 0. Okay. Now next, consider the third point. We want a desirable cutoff frequency. Let it the point x. This is point x. Okay. So if you consider this one and this one, which we have drawn in the previous case, over here we will be having maximum frequency, maximum amplitude, and at pi we will be having the minimum or the 0 amplitude. Now I want to have the cutoff at a particular frequency component. In the previous second and the first cases, if you see, we do not have a control. Okay, so we have just placed a pole in the first case, and whatever the cutoff frequency is there, we have accepted that. Okay, in the second case also, we have placed a pole, and at pi we have placed a 0, and whatever is the cutoff frequency, we have accepted that. Okay. Now, what happens is that when I want to manipulate the frequency response so that I can get a low pass filter which is having a particular cutoff frequency. Okay, so what to do? I will have to use additional poles or zeros or both to get to that position. Okay. So usually what we do is that we can decide the roll off. We can decide the roll off by adding 0 at particular locations. Okay. Now the problem is that when I have added a 0, what has happened? The system becomes non-realizable because the number of the poles, it has become lesser than the number of the zeros. So to have that condition, to meet the condition of the realizable filter to be met, we should add another filter, another pole onto the existing pole. So at this location, we will be having two poles. We will be having two poles. Okay, are you getting my point? Now, since we will be having the two poles, now the system becomes realizable. So what happens over here? We start with a square. Why a square? Because at D, if you look into the D, we are having D1, D2, but D1 and D2 are same because both the poles are at the same position. So it starts at a square, and then at the position X where we have put the 0, it becomes 0, and then we get a ripple at this position at a pi. Okay. Now next what? Next, if we look into the fourth case, what we have done, I have taken out one of the poles from this location and I have put near to the cutoff frequency where I want. So in this case, this amplitude a square value, it is not a square, but it would be given by 1 by d1 d2. Okay, so you can consider these responses as the normalized responses, because if I do not normalize, then I will not be able to compare both the things, because the gain at DC frequency will be different. Okay, so when I assume to be normalized, then this point becomes 1. Okay, now if you look into the frequency component, what is happening? If you trace this amplitude, this thing, if you see, it has become more steeper in nature, right? And now if you look into the cutoff frequency, previously say it was at pi by 2, now it has shifted towards the right. Okay, if I bring this pole more nearer, I will be getting a more steeper kind of response. Okay.
So what's the benefit of that? We are getting a steeper response, right? What's the benefit of that?
Steeper, if you look over here, the ideal response, it should be like this. Okay, now in the previous case, that is the first advantage, that as you place closer to each other, you are by playing the distance, you can fix your own this cutoff frequency. First advantage. Okay, first is that idealness. Second is you can choose your own cutoff frequency by playing with the distance. These two are the advantages. Third is, if you see in the first case, what is happening? There is a slow decrease just from the starting of the filter response. However, in the passband region, when you are placing in the fourth case, if you see in the passband, the roll off is quite slow. That means your signal component will be more stable in the filtered signal. Okay, यहाँ पे क्या हो रहा है? We are saying that at by root 2 आपका cut off frequency you are having, but if you look in over here, what is happening? The signal is losing its power, and it is losing its power very rapidly. Okay, so whatever the output you will be getting, there will be some distortions within the signal itself, frequency dependent distortion, but usually this happens in any of the filters and we accept that distortion. Okay, but when you are getting a very high roll off, like in the fourth case, what I have shown you with the this green response. In this case, what happens is that क्या होगा? In the passband, you are having relatively stable input. Output. Okay, so distortion, frequency dependent distortion would be minimized to a certain extent. It would be there, but it would be minimized to a certain extent. Okay, so this was about the low pass filter. Okay, now with that analogy, if you look into the high pass filter, you can have an high pass filter like this. So if you see at low component, there will be some values, residual value, okay, which can be eliminated by placing a 0 at 0. Okay, third case again उसका उल्टा ही है, basically it is the opposite, and then in this case you will be having this rule of something like this. This one is for the fourth case. So you will be able to correlate with the low pass filter frequency response. Okay. When we have band pass filter, you can use two poles. So at 0 and pi, there will be some frequency component gain. If you place two zeros over there, then at 0 and pi, you will be having this thing. Then band reject filter. So if you do not consider the red poles, only consider the blue poles and zeros, so we will get some amplitude value, something like this. Now if to these filter, if we add some two more filters, two more poles, two more poles, so the response becomes steeper. Okay, then coming to notch filter, over here if you see at pi by 2, say we want to create a notch filter which will stop the frequency components present at pi by 2. So at pi by 2 we will put the zeros, so again we will get some response like this. Okay, so see how just by placing the poles and the zeros we are able to design different types of filters. Okay, Any doubt till now? Shall I move forward? Now coming to the radial positioning. Okay, radial positioning we have uh, talked about, not basically the radial positioning but the positioning of the poles and the zeros in the S plane, where we have seen that if we move the pole horizontally away from the frequency axis, what happens? Its effects on the frequency axis, it decreases. Okay, the same was with the zeros also. Okay, now herein we want to study the same thing, but we are telling that we want to look into the effect of radial positioning of the poles and zeros onto the filter response. Why radial? The name radial, it comes from radius. Okay, now in the Z plane, if you see, we are looking into the resonating frequency at a particular radius. Say for example, if I place a pole over here, say at 45-degree angle, so I can change the radius, and by changing the radius I can play with the amplitude at the resonant frequency. I can vary the amplitude at the resonant frequency, and that effect will be the maximized effect by that pole over there. Okay, why maximization क्यों होता है? Because that is the shortest distance. Okay, so across the radius you will be having the shortest distance. Okay, now let us take some examples. In the first case, we have pole at 0.9. In the second case, we have pole at 0.5, and in the third case, we have pole at 0.3. Okay, so what happens? What happens? So in the first case, h of z, it will be equal to 1 by 0.9. Sorry, 0.1. It would be 0.1. In the second case, it would be 1 by 0.5, and in the third case, hz would be modulus of hz it would be 1 by 0.7. It would be 1 by 0.7. So what are the values? This will be 10, 2 आ जाएगा, and 1 by ये करो कितना आ रहा है? 10 by 7, 1.33 something like that. 1.28 10 173. हाँ 28 ना, हाँ 7 4 is 28. 1.4 so 1.42. So if you see, as we are moving ahead or moving away from the zero frequency component, we got 0 to 1.42. Okay. Similarly, if you look at the pi, it would be different, but herein we are only and only interested in the resonant frequency. For the sake of understanding what we have done, we have only taken the positioning of the poles at the real axis. Okay. The same type of activity can also be observed if you change the radius. You change it over here, if you change it over here, wherever you want to go. So at the resonant frequency, you will be getting similar type of thing. Hearing, since we have placed it onto the real axis, positive real axis, we have basically designed a low pass filter, and hence we have got a low pass filter signal. In the exam, I can tell you that you try to find out what would be the effect if you want to of the effect of radial positioning of the pole if you want to design a band pass filter. Okay, so what you will do, you have to put it somewhere at other locations so that you get a maximum value somewhere in between 0 and pi, that you can decide. Similarly, if you look into the zeros, I can put the value at 1, 0 0.5, 0 0.3. So modulus of h of z, it is equal to 1. In the second case it is 0 0.5, and in the third case 0 0.3. Okay. At the DC frequency. Okay. At the DC frequency, we have put a pole over here because otherwise the system will become an unrealizable filter, but we just want to look into the effect of the zeros. Okay. Now I can give you some filters having different at least one poles and one zero, and I can ask you analyze the frequency response of the filter through mathematical expressions. So what you have to do, again, what is modulus of hz? You are having r1 r2 divided by d1 d2, considering this filter, it is having two zeros and two poles. Okay, two zeros and two poles. Okay. So you have understood what is meant by the radial positioning. Radial positioning means you have this radius up to omega naught. So you can place the poles at different positions across this radius, and then you analyze the filter response. Okay. So if you look over here, what we have basically seen is that as we place the poles nearer to the your resonant frequency axis, no, resonance frequency component point, your frequency axis, we get an enhancement of the amplitude. Okay, as we move that towards the zero, towards the origin of the z plane, towards the origin of the z plane, as it is the case at the case 3, where p is equal to 0.3, but we have the frequency response or the amplitude values, they are decreasing. Okay, so as the distance increases, the amplitude decreases. Similarly, if you look in the case of the zeros, as the distance increases, what is happening? Your suppression component initially it is having higher amplitude, and slowly as you are moving away, the amplitude value they are decreasing. Okay, so in other words, if you combine these two, what we can say? We can say, oh sorry, this one would be, sorry, this one would be 0, na? 0, and this is 0.7. Distance, na? Distance between the year. So what is happening? So the amplitude is increasing, right? In the first case, in the case of poles, the amplitude is decreasing, and in the case of zeros, the amplitude is increasing. So by combining these two, what we can say? By combining these two, we can say that as we place the pole and the zero toward near to the frequency axis, there is an increased activity of the pole and the zero. Suppose I give you with poles and zeros, and I give you the positions like here. So in the first case, if you see, 0 is at 0.9, pole is at 0.9, and 1 is at 0. In the second case, what we have, 0 and pole at 0. And lastly, we have 0, 1 pole here, 1 0 is also here, and then 1 pole at the origin. Okay. So what happens if you look into this modulus of h of z 0, it is 90, then 1.9, 1.9. At pi, what is happening? 0.05, 0.1, and 0.1. Now if you look at these two locations, what is happening? The amplitude values are totally same. Why this is so? If you compare this, 0.9 and 0, 0.9 and 0, these are there, and then we have placed a pole and a 0 at the same location, so they are cancelling each other. So if you look into their transfer function would be given by z of minus of 0.9 and z of because of the 0, z minus 0, which is z, then multiplied by z minus of 0.9. So we get this as the transfer function, where this is for the realization of the filter, and this equation it is used for the calculation of the pole and the zeros. Okay. Similarly, over here also you have the transfer function given, and at last, if you see, we have this as the transfer function. Now it is interesting to see over here that you will be very intrigued to cancel out this one and this one when you are trying to calculate the poles and the zero. But please do not do that. Why? Because if you are doing that, then you are eliminating 1 0 and a 1 pole from the mathematical expression itself. So when you will be calculating the positioning of the poles and the zeros, you will be missing 1 pole and the 1 zeros. So that would make your result incorrect. Okay. And also, when you go for the realization of the filter would look something like this and not like this. So your realization will also be incorrect. Okay. So since the time is short, so I would ask you to calculate the amplitude response at pi by 4, pi by 2 and 3 pi by 4 tomorrow and submit you in the class notebook only and submit it tomorrow. The similar thing, just with you see, we have added one extra pole over here. How this extra pole it is affecting, we have looked into the thing. If you see, when we are placing another extra pole at a particular location, what we have, see, there is a 10 time increase in the amplitude response. Okay. So what happens when we place a pole over a 0, something like that, it's over here, 0.908, two zeros at one place. When we place two zeros at one place, how it affects the gain of the circuit. Okay. Now, from the next class, we will be starting with this thing, what it was, the actual filter design. We'll start with the FIR filter design. For that, you will be needing this equation. So, if you are given with some xz, so what you have to do, 1 by 1 plus a z inverse. So, we have to convert it into the omega t, because we are while trying to figure out the amplitude response of any given filter, we are mainly interested in the frequency axis, right? And hence this z inverse, it has been replaced with e to the power minus j omega t, which is basically the equation for the circle. Basically, we are working on the unit circle. That's why. Now again, when you break it down, you get a real component and an imaginary component. So it is in the form of 1 minus jb. So you multiply both the numerator and the denominator with the conjugate of that number, and then you get capital A plus jb. This format you can get, because uh, this one it would become a square plus b square in the a square plus b square form, right? So you, from here you can get a by a square plus b square plus j of b by a square plus b square. So you get a real and an imaginary component, and from there, if you try to find out the amplitude response, it is just basically the under root of a square plus b square. And phase, how to calculate the phase, I have already told you in the previous class. Okay. There was this chart. This chart, it was it has already been told to you. So what would be your output and the phase response? You have to calculate using this. Okay. So with this, we complete this basics of digital